Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to show that confounding factors can completely distort the causal effects that we see in data to the point where they might lead us to make the opposite conclusion to what actually is true. This is called Simpson's paradox and it happens all over the place. In particular, we're going to focus on an example where we look at 3-point percentage of NBA players. Let's get to it. So in particular, we're going to compare two NBA players, Courtney Lee and Stephen Curry. All of this started because I came across a data set which had 3-point shots from many players that took place in the NBA in the 2014-2015 season. And I checked out the 3-point percentage of some of them. And in particular, I was surprised that when I looked at Stephen Curry's 3-point percentage, it was 41.7%, which is really good. But when I looked at Courtney Lee, who was playing for the Memphis Grizzlies, I believe, in that season, it was 43.9%. So someone that, doesn't follow basketball very much might be tempted to think, I guess Courtney Lee shoots 3-pointers better than Stephen Curry. So the question here would be, was Lee a better shooter in the 2014-2015 season than Stephen Curry? If you follow basketball, I guess you already see where I'm going. Just in case you don't follow basketball, I'm going to show you a short clip of even if you don't follow basketball, let me tell you. So Stephen Curry was named MVP, most valuable player in that season. The Warriors, his team, won the NBA, in a large part because of how well he shoots 3-pointers. And so he was the most valuable player. He's essentially a shooter. So the thing that he does best is shooting 3-pointers. It is therefore very, very surprising that we see that another player, who was obviously also a fantastic player, all my respect to Courtney Lee, but whom a lot of you might not have heard about, has a higher 3-point percentage. So what is going on? Let us dig a little bit deeper into the data. So here I'm going to separate the 3-pointers between short threes that happened very close to the NBA 3-point line. They're at 24 feet or closer, and long threes, which are longer. So for short threes, what we see is that Stephen Curry makes half of them, half of his of his short threes. Courtney Lee makes slightly less than half. So Stephen Curry shoots better from close than Courtney Lee, at least from this data. Let's see what happens for long threes, so longer than 24 feet. It turns out that Stephen Curry shoots them at almost 40%, which is really impressive. This is long threes tend to be more difficult. Courtney Lee shoots them at a little bit less than 35%. So what we see is that Stephen Curry shoots better from close and better from far. But when we aggregate all the data, what we see is that Stephen Curry has, again, 41.7%. This is his 3-point percentage. And Courtney Lee has 43.9%. So what is going on here? Stephen Curry shoots better from close and better from far, but shoots worse overall. That seems very, very strange. So today we're going to explain, this is called Simpson's paradox, because it does sound a bit, I was going to say paradoxical. I don't even know if that word exists. It does sound like a paradox, right? That he shoots better from close and also from far, but worse overall. That sounds very strange. Maybe by looking at this data, you can already see what's going on. But before explaining exactly what's going on, we have to analyze this problem from the viewpoint of causal inference. So from the viewpoint of causal inference, we're going to treat this 3-point shot as the observed variable that we're going to base our causal inference on, we're going to represent whether the shot goes in or not as a Bernoulli random variable that is equal to 1 if the shot goes in and 0 if it does not go in. And then we have a treatment. So treatment in causal inference is usually whether you give someone a drug or not, or whether you give someone a vaccine or not. Here it's going to be whether Curry or Lee shoots the three-pointer. And essentially what we want to see if there's a causal effect for the same three-pointer. If Lee shoots, is it more likely to go in than if Curry shoots? That's really the causal effect that we're after. Okay, so if t is equal to Curry, the shot is being shot by Curry. If t is equal to Lee, the shot is being shot by Lee. And what we see from observed data is that the probability that a three-pointer is made if Curry is taking the shot is smaller than the probability that the three-pointer is made if Lee is shooting the shot. Okay, and that's what we're surprised about. Given that we're surprised about it, we should ask ourselves what these conditional probabilities actually mean. Okay, so what they do mean is that from all his three-point shots, Curry makes 41.7%. There's no discussion. That is exactly what this means. Similarly, from all the three-point shots that he takes, I hope I said that right for Curry, that he takes, Lee makes 43.9% of his shots. Absolutely no discussion. However, it's perhaps even more important to emphasize what this does not mean. What this does not mean is that if Lee had taken Curry's shots, then he would have made 43.9% of them instead of 41.7%. Why is this not true? It's not true because the shots taken by Lee are not the same as the shots taken by Curry. And we're going to make that very precise in a moment. In order to make things precise, we're going to define the potential outcomes associated to this causal inference problem. Remember, and there's a video about this in case you want to refresh your memory, but the potential outcome associated to Curry essentially captures a hypothetical scenario where Curry was shooting every possible shot. Okay, of course, we're never going to be able to observe this because he shoots only some of them, but we're going to imagine, what if Curry shot all of every possible shot? What would be the probability that he makes the shot? In that case, the potential outcome is equal to 1, or he misses it. The potential outcome is equal to 0. Similarly, we're going to have another random variable, which is a potential outcome associated to Lee that represents this hypothetical scenario where Lee is shooting every possible shot. Okay? If it's equal to 1, Lee makes the hypothetical shot. If it's equal to 0, he misses it. All right. What do we actually observe? We observe the potential outcome associated to Curry when Curry shoots, because there we see if he makes it or not, but not for the other shots. Okay? Similarly, we observe the potential outcome associated to Lee if Lee shoots. If he doesn't, then we're not going to see them. Okay? What we're really after is knowing whether if Lee shot all of the shots, would his percentage be higher than Curry's if Curry shot all of the shots. Okay, this is what we really want to know. That would mean that indeed Lee was the better shooter. And the challenge is that, of course, we cannot see these potential outcomes simultaneously. What do we see? Well, here we have some columns indicating the treatment. So the treatment tells us that Curry is shooting this particular shot. The observed outcome is that he misses. What does this tell us? It tells us that the potential outcome for that shot is equal to a miss. What does it tell us about the potential outcome associated? So this was the potential outcome associated to Curry. What does it tell us about the potential outcome associated to Lee? Nothing. We don't know if Lee would have made that shot or not. And that's the critical challenge here. Another shot that Curry takes, in this case he makes them. Again, we have no idea whether Lee would have made it or not. Okay, now Lee is the one taking the shot. He makes it. We don't know whether Curry would have made the shot. We have no idea, but we do know that Lee made the shot. So in this case, we are seeing the potential outcome associated to Lee. We're not seeing the potential outcome associated to Curry, and so on and so forth. So these question marks here indicate potential outcomes that we're not observing, because if Curry takes a shot, then we don't know whether Lee would have made it or not if he was taking it. Those are called counterfactuals in the causal inference lingo. And they're counterfactuals because they're against reality. Lee didn't take the shot, but still it's important to define them so that we can actually define the causal effect that Lee is a better shooter than Curry. Okay, so now what can we get? Can we actually infer from the data what we want to infer, which is the probability of these potential outcomes? Well, what we have is the percentage of shots made by Curry from the shots that he actually took. Similarly, we have the percentage made by Lee from the shots that he actually took. Are they the same as these probabilities that we are after? Well, let's take a look. We know for sure that they're the same as the probability of the potential outcome being equal to 1, conditioned on that particular player. So if Curry shoots, then this percentage indeed tells you the percentage for the potential outcome that Curry shoots, conditioned on that he's taking those shots. This is almost tautological. It's just saying for the shots that he takes, we know that's the right percentage. That's fine, right? Same thing for Lee. If we condition on Lee, we're saying Lee takes those shots. Those are the shots taken by Lee. Among those shots, we're pretty sure that's a good percentage. But is it representative of all the shots? For that to happen, T and the potential outcomes should be independent. So here it's important to realize that we're not saying that T and Y are independent, okay? That's for sure, that doesn't make any sense because Y is the observed outcome. Here what we're saying is, if we look at the percentages that tell us whether Curry or Lee would make every shot if they tried it, is that independent from the choice that they are taking this shot or that shot? So this would be independent if the shots made by Lee and the shots made by Curry were essentially similar, in the sense that, so this can be achieved, for example, by doing the following. Every time someone is going to take a shot, we flip a coin, we randomize, we flip a coin and we say, oh, it's Curry's turn. Curry's going to take this shot. Then another shot comes along, oh, we flip a coin, now it's Lee's turn. Lee's going to take a shot. This is what we do in a randomized control trial when we're trying to evaluate vaccines and so on. Obviously here it's completely impossible. But if we manage to do that, then it would be true that the potential outcomes would be independent from the treatment, from who the shooter is. And that would mean essentially that no shooter is taking more difficult shots than the other shooter. They're taking essentially the same kind of shots. If that happens, then this equality holds, and we can say that the one that has the higher percentage is the better shooter. So now we need to ask, is that true for this data set? Is it true that they're taking the same kind of shots? So now we go back to the data, and we see that the shot distance D actually plays a very important role in the types of shots that they're shooting. So the first thing that we realize is that if we look at the fraction of short threes taken by Curry, it's around 20%. The fraction of short threes taken by Lee is around 68%. It's much, much, much higher. Okay. Similarly, we see that Curry and Lee shoot short threes. Here we're also conditioning on short threes apart from the shooter. They shoot them much better than long threes. Okay, almost 10% better, like really significantly, and actually more than 10% better in the case of Lee. Okay, like they actually shoot them much, much better, both of them. So again, Curry is taking many more long threes, many less, that's not even English, less short threes, but short threes are much easier. Okay, so what do we conclude? We conclude that the potential outcomes depend on the distance, because it's easier to make shorter threes for both of the players than to make longer threes for both of the players. And the distance depends on who the shooter is in the following sense. We know that Lee is taking many more short threes than long threes, and the opposite is true for Curry, okay? So because of that, the potential outcomes are definitely not independent of the shooter. In other words, the type of shots taken by Curry are more difficult because they're longer threes, okay? And the types of shots taken by Lee are easier because they're shorter threes. So we cannot directly use these percentages that we're observing from the data to conclude that Curry is a worse shooter than Lee. Okay, we cannot do that. Let's make this really, really very clear, the effect of distance as a confounding factor. If we look at the observed percentage for Lee, we can separate it between the short threes and the long threes. Okay, this is just by the law of total probability. And now we use the chain rule to expand this, and we see that we have this weighted sum where we're weighting by the probability that Lee shoots short threes and long threes. And that is multiplying the probability that he makes the short threes and he makes the long threes. So what is happening here? What is happening is that his overall percentage is going to be boosted by the fact that he's taking the easy shots much more often than the difficult shots. Okay, and that's how he achieves this overall percentage of 43.9%. Now what happens, we're going to put this up here to compare. Now what happens for Curry? So Curry, again, we're going to separate into short threes and long threes, and then we apply the chain rule to have the conditional probabilities. And here we have, this is also weighted by the probability that he shoots a short three or the probability that he shoots a long three, okay? And that's multiplied by the percentage of his short threes and the long threes. And we see that here the opposite thing happens. It has a very small percentage of short threes, very high percentage of long threes that are more difficult and that would have a lower percentage for both players. So this is bringing his percentage down to this 41.6%. And that's essentially the explanation for Simpson's paradox. There's this confounding factor that is distorting the apparent 3-point percentage of both players. Okay. So how can we adjust for it? Now we know that the distance is kind of fooling us into thinking that Lee is the better 3-point shooter. How can we correct for that? Well, we can multiply. Well, what we want is the potential outcome, right? So what we can do is we can say, oh, how does Curry shoot his short threes? How does he shoot his long threes? Now I'm going to multiply not by the fraction of short threes or long threes that he takes, but by the fraction that a typical player takes, which we can do. We can estimate from our data by just seeing in general for all players what is the percentage of short threes or long threes they take. In this case, we're just considering these two players, so we're just going to pull all the short threes and long threes from the two players. All right, so I already answered this question that I was going to ask you. Sorry about that. Do we know the probability that someone shoots a short three or a long three? Well, we pull together all the players and we say, what's the fraction of short threes? What's the fraction of long threes? A more critical question is, do we know the potential outcome of Curry conditioned on distance? So let's take a look. The answer is that we do under the following assumption. We say that the potential outcome of Curry and the choice of who shoots that shot are conditionally independent given the distance. This is essentially the same idea as we discussed before with independence, except that now we're conditioning on distance. So what we're saying is, if we know this thing is a short three, and we look at Curry's short threes and Lee's short threes, they're essentially the same difficulty. There's no additional confounding factor that's causing a systematic difference between them. And same for the long shots. We're going to assume that among the long shots, if you look at Curry's long shots and Lee's long shots, they're essentially the same difficulty. There's no systematic difference between them. Okay? If we assume that, and we'll come back to this assumption in a moment, if we assume that, then we see that the observed percentage for Curry when he's shooting short threes by definition is equal to his potential outcome when he's shooting short threes because we observe them. But now because of independence, this is also equal to the potential outcome just conditioned on the distance. So this is saying because the shots in general taken by Lee and Curry, if they are short, are kind of the same, this percentage is a good estimate of the percentage of how Curry would shoot if he just shot all of the short threes. Similarly, this is 0.5. Similarly, same thing for long. We're assuming conditional independence, so what we're saying is the percentage that we observe is representative of the percentage that we would see if Curry shot all of the long threes, because we're assuming that he's shooting the same kind of long threes as Lee. Okay, so then this percentage we can use. And this is great because we are going to go back to the formula, and this will allow us to compute the potential outcomes for Curry. So we're going to assume exactly the same for Lee. His shots are the same as Curry's as long as they're either short threes or long threes. So the observed probability of a short three, given that that Lee is shooting it, is going to be, because of that same argument, the probability that the potential outcome given Lee would be 1, conditioning on it being a short three, which in this case is 48.3%. And similarly, when we look at the percentage achieved by Lee for long threes, we think that that's representative. That really indicates what would happen if he shot all of the long threes. All right, and that percentage would be 34.5%. So this is great because now we can go back to our formula. We know this. Here we are just going to use the fraction of short threes and long threes for all the players, these two players that we're considering. And here we can use the observed 3 percentages by Curry and aggregate them, because we're assuming that once he shoots a long three, that's kind of a typical long three for all players. Okay, and when we do that, realize that now we're not multiplying here by the fraction of threes taken by short threes taken by Curry and long threes taken by Curry, because this was what was distorting it. We're multiplying it by the fractions that all players take. Now we get a number which is 43%. Okay, this could be like the corrected 3-point percentage if we're only taking into account distance. And this is much higher than the one that we had observed just from the data. Why? Because he was taking more of the difficult ones. If we do the same for Lee, what we see is that we're again multiplying by the same fraction here, and that's crucial, right? We're correcting for the fact that he shoots easier shots in general by just like using the same fraction for both players. And now the fact that he shoots short threes worse and long threes worse is going to hurt him in his overall percentage. His corrected percentage is still amazing. It's 39%, but it's much smaller than the one we had observed from the data. And in particular, it's significantly smaller than Curry's. So now, let me ask you, is this assumption correct? The assumption that we're using to obtain our corrected 3-point percentage? Maybe pause the video and think a little bit about it. The answer is no. No, as you saw in the clip at the beginning that I showed you, you could see like the whole other team essentially hunting down Curry and just jumping, putting arms, like doing whatever it takes to stop him from shooting. And that's what other teams do, because you know, Curry's shot is like one of the most lethal weapons in the NBA. So of course the other team is completely going to scheme to try to avoid him shooting. He's going to end up taking very difficult shots, even if they're short threes. So the three that we saw at the beginning of the video was a short three, but it was of insane difficulty, right? Off the dribble with like 3 people on top of him. And he just takes these kind of threes all the time. So we have adjusted for one confounding factor, which is distance. He takes long threes more often just because, you know, the defenders don't have time to get to him. But there's added confounding factors, which would be how long does he have to shoot because players are kind of jumping on him, the quality of the defenders, or whether he has 2 defenders on top of him or just 1. Okay, so we're not accounting for all of that. And even like that, we already see that his percentage is significantly higher than a really good shooter like Lee. So imagine if we took that into account, right? So nevertheless, is this a better measure of shooting ability? The answer is yes, for sure. And this is a common theme when we're doing causal inference from observational data. At the end of the day, we're only going to be able to adjust for some of the confounders, some of the confounding factors that are distorting the conditional probabilities that we are seeing. So we cannot guarantee that there's no other confounding factors that are distorting them further, but it's still better to correct, right? You're still going to get a better idea of what reality is like if you actually correct for things that you should correct. And of course, ideally, the follow-up should be to do some kind of randomized trial. In this case, it's of course impossible because they were playing even for different teams. You cannot just say, okay, now in this NBA game, it's Lee who's going to shoot instead of Curry. It's impossible. Observational data is all we have. We need to gather as many additional data as we can, try to think about what could be confounding factors and how to correct for them. All right, so that's all I got. What have we learned? We have learned that causal inference from observational data is very challenging, to the point where the confounders can severely distort the conditional probabilities and show the opposite effect to what is actually true, and that's called Simpson's paradox. And we have also learned how we can adjust for those known confounders in order to actually detect the real causal effect, of course under this conditional independence assumption. Thank you very much.